Good morning, everybody. Today we'll learn about the electromagnetic radiation, the Fourier transform infrared spectroscopy. Then we'll go one after another slide. I will come to know about the fundamental of the Fourier transform infrared spectroscopy. So how it is going to change and how it affects. So in the electromagnetic radiation, there are defined type of radiation and different type of vibration that is works. It is going to go from radio wave to microwave, infrared spectroscopy or infrared UVs, X-ray and gamma ray. So the frequency is going to be lower to higher from radio wave to gamma ray. So as we are going to discuss with the infrared today, the first one, that is what is going to be changed. The total energy of the molecule, that is transitional, electronic, vibrational, rotational and nuclear energy. So if it is that, how that is going to be changed, that we are going to start. Electronic energy, that's a transition energy, transitional energy, that's the UV visible or X-ray. The vibrational transition, that's the infrared that we are going to discuss today. The rotational transition, that is a microwave, and the nuclear spin or the NMR or nuclear magnetic resonance spectroscopy. So we will go one after another each and every day, one after another slide or one after another lecture. So let's start. The electronic energy, that's the transition in the UVs, that to the infrared, there is a vibrational transition of a molecule, that is basically diatomic molecule that can show the infrared. Now, how the infrared spectroscopy is used and why it is used for the identification of the organic molecule. And IR spectrum provide the 100% identification of the spectrum that is matched. Except that if not, IR is at least providing the information about the types of the bond present in the molecule. And it is easy to use, and the instrumentation cost, that is also very cheap compared to other instrumentation that we need to in the chemistry or any physics lab. So next one, what is done in the infrared spectroscopy? It is used to measure the vibrational frequency of the bond in the molecule. So first we need to know bonds are not rigid. It works like a spring, viewed as a spring with a weight at each end. Each bond has a characteristic frequency, and the IR scan is ranges in the frequency in the infrared spectrum region in the electromagnetic spectrum. Any frequency which matches the characteristic frequency of the band will absorb the frequency in the electromagnetic radiation and will show us about the frequency in infrared. So that is told, it is like a spring. Let's compare about the diatomic molecule over here. Here's the diatomic molecule, and it can be compressed or can be stretched, like stretches and stretching and compression of our diatomic or biatomic molecule. So what changes in that one? It's stretching and compressed. It changes the energy of that, or due to the energy changes, as well as at the same time it changes the dipole moment. That is the main factor for the infrared spectroscopy that we look at. The change of the dipole moment during the stretching and the compression or the stretching of the spring or the diatomic molecule. So next one. So due to the change of the dipole moment, the two types of molecular vibration we see. One is stretching, one is bending. If it is stretching, in that case, if the n numbers of atoms are present in the molecule, there are the 3n numbers or degree of freedom we can expect, and or at least same. In the nonlinear molecule, 3 is the 3 degree of rotational, 3 are the transitional, and the remaining corresponds to the fundamental vibration. And in case of nonlinear molecule, 3 degree are the rotational, 3 are transitional, remaining corresponds to the fundamental vibration. In case of linear molecule, 2 degree of rotational and 3 are the transitional. So the vibration, this is a synopsis that we talked in the previous slide. That is the total 3n minus 6 are the nonlinear, in case of nonlinear molecule, number of possible mode of vibrations. In case of linear molecule is 3n minus 5 number of vibration that we expect in a linear or what are those? Mode of vibration stretching that we just talked about, except that in the bending mode of vibration, stretching there is symmetric and asymmetric. And in case of bending, there are four different types. One is scissoring, like this. One is rocking, like this. It is going to work like that. Then wagging, that is just like this. Not even rocking is like this. Wagging is like this. Now, next one that is known as the twisting. The two different sides. The two atoms are going, the central atom is here. The two atoms are going back and forth like this. That is the twisting. Now, here's the range of the frequency in the stretching and bending. It is expected and that is saying that stretching frequency is higher in energy compared to the bending one. Here we say the stretching one, that's the top one, the stretching frequencies, and the bending frequency, that's the bottom one, that is the bending frequency, which is lower in energy compared to the stretching. Now let's go with one example, that's the carbon dioxide. What it says, the carbon dioxide is the linear and hence is a 4 fundamental vibration, 3n minus 5. N is the number of atoms, that's 3 atoms are there, 1 carbon, 2 oxygen. 3 into 3, 9, minus 5. 3n minus 5, there's a 4 number of defined vibration that we see or we can see in the infrared of the carbon dioxide. The two of the scissoring or the bending vibration and equivalent and therefore have the same frequency and the same to be degenerated approaching in the infrared as at 666 centimeter inverse right. Here is a pictorial representation of the bending and stretching vibration. If you follow the arrow of the carbon dioxide, that we get that. Now, one very important thing, here you can see at the last part of the slide, there are different molecules, the diatomic molecules, carbon monoxide, iodine chloride or chlorine iodide. Both of them are basically absorbed the infrared. Whereas the hydrogen, nitrogen, the diatomic molecules, similar like the previous two molecules, carbon monoxide or iron chloride, but they don't show the infrared spectra because it doesn't change the dipole moment during stretching at all. So that's why that's a very important part to remember. Stretching frequency of bond can be approximated by the Hooke's law. And in this one, the frequency that depends on the spring strength or the bond stiffness and the reduced mass of the molecule. That is represented in the equation over here. And it shows that directly on the strength of the bonding between the two atoms it depends on, and that is represented with the nu. The inversely reduced mass of the two atoms, and after all expected that nu will increase with increasing bond strength or bond order and decreasing mass. Now the main thing, the factors that are responsible for the shifting of the vibrational frequency from their normal value, those are dependent on the 6 different things or different issues. There's a coupled vibration, Fermi resonance, bond order, electronic effect, hydrogen bonding, and bond angle. That so first one is a coupled vibration. What it says in the coupled vibration, that is basically how it is going to go, that we just talked about symmetric and asymmetric vibration. And according to that, it says that if it is a CH bond, in case of methylene group in the CH bond, two absorption occurs that corresponds to the symmetric and asymmetric vibration. In such case, asymmetric vibration always takes place at the higher wave number compared to the symmetric vibration. These two are known as the coupled vibration because this vibration occurs at a different frequency than, than that requires for the just CH string. Then the next one is the Fermi resonance. That is about mostly it is basically explained with the quantum mechanical calculation. But theoretically, what we can say in the Fermi resonance, this one the couple of pendulum is like that in infrared spectrum. Absorption band are spread over the wide range of frequencies. It may happen that the energy of the overtone level changes the coincide with the fundamental mode of the different vibration. It can be seen as the type of resonance takes place as in case of coupled pendulum. This type of resonance is known as the Fermi resonance. For example, in case of aldehyde group, the CH stretching absorption usually appears as a doublet around 2820 and 2720 because of the interaction between CH stretching. There is a fundamental bend and the overtone of the CH deformation. There is a bending. Now the third one, the effect of bond order. That is basically the hybridization. In this one, the hybridization, it is known that the larger the S character, higher is going to be the band frequency. So if we go from sp3 to sp, the S character is going to increase and P character is going to increase. Similarly, in sp3, the S character and P character are like 25% S, 25% P. In sp2, 33.33%, each of them. But in case of SP, both of them are 50%, 50%. So the higher the S character, higher the band frequency. Here, you see, in the triple bond, there is the SP, there is a higher frequency compared to the sp2, or later on, there is a SP. So that's the way the bond order or the hybridization going to change or changing the frequency of the bond. Now, the important one, the most important, the electronic effect. Electronic effect. The one is a resonance or the mesomeric effect, and the next one is the inductive effect. The first one, the electron donating group affect that or the decrease the frequency, and electron withdrawing group increase the frequency. Here in the example, we say inductive effect increase the C double bond O. There's a keto group frequency, strength of the frequency, strength of the bond is higher, and the frequency is going to be higher. Here the electron withdrawing group, that is a chlorine group or chloride group, is here, and due to the presence of the chloride group here, the inductive effect is going to affect it, and it is going to increase the frequency of C11O. Similarly or simultaneously, if it is a electron donating group, there is an amine group or the keto group, OR or the NR2, those are electron donating group. Due to the presence of the resonance effect of the lone pair of the oxygen or nitrogen over here in the amine group, that is going to decrease the frequency of the C double bond O. That is known as electron withdrawing group effect over the C double bond O in the frequency. So what we come to know that the inductive effect, electron donating group or the plus M effect decreases the frequency, and electron withdrawing group that increases the frequency. The next one, few example of that one, there's a synopsis of example. If we go from right to left, follow here. In this one, from 1850, it is going to decrease up to 1650 or 1690 due to the presence of electron withdrawing group, and after all, due to the resonance of the amine group. From chlorine to OR or the keto group or the ether group, and after that the amine group, that NR2. It is going to change from right to left due to the presence of different groups. So inductive effect or electron withdrawing effect, electron withdrawing group disfavor the resonance structure. The result is overall bond being stronger, therefore the strengthening the frequency is higher. Resonance effect, the electron donating effect, the lone pair of electron donating favor the resonance structure. This result in the bond being weakened, therefore the stretching frequency is lower. Here is the one list of that one, or these two are basically competing each other at the same time. Chloride group, that is the inductive effect, dominate stronger over the electron donating group is stronger. Electron withdrawing group is higher in case of chloride group. In the ether group or OR is a moderate electron withdrawing group and the moderate electron donating group. So there are not much effect of both of them at the same time. And in the amine group, the resonance effect dominate. It weaken the C double bond O bond. So substitution that reduces C double bond O lengthen and increase double bond character, increase the frequency of C double bond O and vice versa. Now the field effect. Here the lone pair effect over here, the ortho substitution compound, the lone pair of electron on two atoms influence each other through space interaction and change the vibrational frequency of both of the groups. That is orthohaloacetophenyl. And this one. Now the hydrogen bonding. Hydrogen bonding decreases the frequency. For example, if XH, X is the molecule, H is the hydrogen, and it is going to make the hydrogen bonding with a B group. That is some basic group or whatever the group it is. What it says that the hydrogen bonding alters the force constant of both groups. That's the nu, or the K. And the XA stretching band moves to lower frequency. The stretching frequency of the acceptor group B is also reduced, but to a lesser extent or lesser degree. The XH bending vibration usually shift to a shorter wavelength. Here is one example of phenol group X, the pH OH. Here OH group is present and this one is going to go through the hydrogen bonding. But here is one thing that we need to know. There are the chances of two. Maybe this one is free or the liquid form, and there's a phenol is present, and another one in the high vacuum or in the vapor phase. In case of vapor phase, we can't expect the hydrogen bonding, and due to the high temperature, high heat, and the band for the phenol group is going to present over here close to 3,500 or close to in between 3,000 to 3,500. But when there is a hydrogen bonding, there is a P1 in the liquid form. Here is a big hump. We can see in between 3,000 to 3,500. That is due to the presence of the hydrogen bonding that we see in the spectrum. Now, the last one, the influence of ring size and bond angle that we'll go through. Here what we get is that if we go from the larger to lower size of the ring, that is in the 7-member, 6-member, 5-member and 4-member ring, here we see the decrease in the frequency 1650 to 1566 in case of butane, but in case of heptene it is 1650. Now in the hexane 1646, then 1611 in the pentene, and in case of butene only it is 1566. Now there is one exception. When it is in propane, it is again increasing to 1656. That is the exception. That never proves the rule. Exception never proves the rule, but that is the exception. Now substitution decrease the frequency. Over here, the butene, methyl butene, dimethyl butene. Similarly, in case of pentene, methyl pentene, dimethyl pentene, hexane, methyl hexane, dimethyl hexane. If we look from left to right over here, say the frequency is going to increase from 1566 to 1675 due to the presence of the substituent, that is the methyl group. Now, conjugation decreases the frequency. In case of phenol group, we know that is the 1625 over here. Now, let's check how it is going to change. Conjugation of C11O or keto group with the C11C. The conjugation of carbonyl with C11C bond shift the value to the lower frequencies. Like for aldehyde, ketone and ester, subtract about 725 to 30 centimeter inverse for conjugation with C11O or keto group. So conjugated ketone shows the frequency 1690 to 1680 centimeter inverse, and conjugated ester 1710 to 1700. It decreases due to the conjugation of C11O and C11C. What is the example of that one? See, over here, due to the presence of double bond, here the electron of the double bond is, or the single bond is going to move over here, and this double bond character of the keto group is going to, the double bond is going to move, or the two electron is going to move over the top of the oxygen. So this C double bond O is going to get a little bit of the single bond character at the same time due to the resonance that lower the frequency of C double bond O. Similarly, of the C double bond C. So those are work simultaneously at the same time. So at the same time, what is going to get that C double bond C is going to C single bond C, so lengthening the bond, and C double bond O is going to lengthening the C double bond O to C single bond character O. So that is going to increase the bond length and decreasing the frequency of the C double bond O at the same time C double bond C. Now, next one, that is about the angle strength, how the angle is going to affect the frequency or the raise the carbonyl frequency. Number one, a smaller angle between the, except the carbon C double bond O, over here we see carbon, there are two other bonds that is attached with the maybe methyl group or any other group over here. So if the smaller angle requires more p character in hybrid forming the ring, in case of ring. Now in response to the more p character of the ring bond, there is a more S character between the C double bond O that strengthen the bond of C double bond O, and that basically increase the frequency of the, or stronger strengthen the bond of the C double bond O and increase the frequency. Now go through the example. Over here, let's say first one, there's the 3-membered, 4-membered, 5-membered, 6-membered, 7-membered ring attached with the keto group. Now look at right to left, sorry, left to right, how the frequency is going to change. 1800 to 1700. The frequency is going to be changed from 3-membered to 7-membered ring with the keto group. At the same time, if we compare, here is the 6-membered ring with the keto group, and over here, not the ring structure. Here the conjugation is going to affect at the same time the strength of the keto group. We'll discuss that one on the next slide. So how that is going to affect the bond strength and going to increase or decrease the frequency of the C double bond O. Factor influencing the C double bond O. That's the ring size that we just discussed over here. The 6-membered, 5-membered, and 4-membered ring. 1715 to 1775. That is the keto group, C double bond O group frequency. Because bond angle is going to increase, then from left to right it is going to decrease. And the ring strength, there's a higher the frequency for the C double bond O. Just we discussed that one. Now other carbonyl group that also affect, that is in case of amide and the lactam. You see the 6-membered, there's a lactam, the NH group here, in 5-membered and the 4-membered. There's a lactam 1660 to, it is going to increase due to the strengthening of the C double bond O from larger ring size or the 6-membered ring to 5-membered to 4-membered ring in case of lactam. Now in the acid chloride, we see it has the frequency 1810 to 1775. Now that's all for today, and we got all the information, the fundamental of the infrared spectra. We'll discuss about the spectrum, all of those in the next lecture or the next teaching that we'll do in the next. Thank you very much. And if you need any help, you can email me back at any time in the email ID that I provided at the end. Have a nice day.